So I will talk about some work done with Shankar and some work inspired by that. So I should first thank Shankar. He was my first point of contact in IMSc. Of course, my mother knew somebody who knew somebody, and I was an undergraduate student very interested in physics, and somehow I ended up in IMSc, and I spoke to a series of people, and then Shankar agreed to mentor me for a summer. He gave me 2 papers that he made me read, and I had great trouble finding him when I wanted to discuss, but then eventually I did manage to figure out how to catch hold of him, and it was very nice. So he taught me the Bethe ansatz in the first summer. Then I came back for 1 semester here, initially working with Bhaskar and then with Shankar on some very nice problems. And then of course we stayed in touch. So over the years, several times I've learned a lot from talking to him. It's usually very, very terse little nuggets of knowledge that he has accumulated over many years that have proved useful in many ways. So the first time I actually wrote a paper with him was just last year, although I have discussed with him for a long time, and that was this. So the work was, a lot of it was done by Shivankar, who's here, my student. So I'll essentially talk about this for now, the first part. And the title can be paraphrased as in this way: in how many ways can 4 vectors add to 0? So we started out with a very complicated problem, but then it ended up, this was the core of it, and it turned out to be very interesting. It's just a geometric problem of 4 vectors that we are all familiar with. 4 vectors in 3 dimensions. If I say they should add to 0, what does that mean? So I'll try to explain this to you. I'll try to say why this is interesting. So let's first think of 3 geometric objects. So here's a dimer, just 2 balls connected by rod. Here are 3 balls connected by rods, a triangle. And here's a tetrahedron, so 4 balls connected by rods. So these are all simplex shapes in the following sense. You take any pair, the distance is the same. Right? Here in tetrahedron, you take any pair, the distance that they're separated by is the same. Okay. So it turns out these 3 are very common motifs in magnetism. Many of the interesting materials in frustrated magnetism are built out of these, one of these, or sometimes even combinations of these. So good. So we'd like to understand each one of them separately and use that as a springboard to understand the physics of magnets, macroscopic magnets. So for magnets, typically we have spins. So you have a spin sitting here, a spin sitting there, a spin sitting there. So a spin is simply a vector with fixed length. So something like this, the length is fixed, it can point in any direction. Okay, that's a spin. For the purpose of this talk, that's all you need to think about. So in each of these cases, you have a spin sitting here, a spin sitting at the vertices, at each vertex, and each pair of spins is connected by a bond of the same strength, because the distance is the same. You take any pair, the distance is the same. Any pair distance is the same. So you expect that the spins interact by this Hamiltonian, by which you mean the energy of their interaction is given by this. You take each pair of spins, you take the dot product, and that's the contribution to the energy. Okay. So here I and j run over all the spins. So essentially it's every pair. You just take the dot product of every pair of spins, and that's the energy. Now this can be rewritten in a very nice way. You can write it as the sum of all spins. It's a vector sum. So you have to add the spins as vectors and then square it. If you do this operation, you see there are some constants, just spin 1 square, spin 2 square. Those are just the lengths of the spins, and those are constants. So they drop out. What remains is just this. Okay. So this Hamiltonian, this energy is the same as this. Okay. So now if I say I have a spin system, let's say I have 4 spins, the energy is given by this. Now just think of it as a geometric problem. The energy is given as the sum of 4 vectors and square. Square is just the length square. Now if I say the energy must be minimum, which is typically what happens at 0 temperature or very low temperature, the energy must be 0. If the energy must be 0, the sum must be 0. Only then you get the minimum of the energy. Okay. So this vector, this is squared, this is a positive quantity. So this vector itself must go to 0. So here you have the simple geometric condition. You have either 2 spins or 3 spins or 4 spins, 2 vectors, 3 vectors, or 4 vectors. And to get the ground state, 2 vectors must add to 0, 3 vectors must add to 0, or 4 vectors must add to 0. Okay. So this already gives rise to very nice physics. So let me give you the simplest example. Suppose you have 2 spins, just 2 vectors here. Okay. So it's just some very simple mathematics, but let me just run you through this. Now, suppose I say there is a vector here and there's a vector there, and then I assert that their sum must be 0. I want to know what the system looks like at 0 temperature. Then I must have one vector pointing, suppose the first vector points this way, the second vector must be in the opposite direction. Only then the sum can be 0. How many such states are there? Okay. Essentially, I can point the first spin in any direction I like, and the second one will automatically follow. So that's the set of all states. So how many such possibilities are there? It's as many points as there are on the surface of a sphere. I can point the first spin in any direction, and that automatically fixes the second spin. So the total number of possible states is just the number of points on a sphere, which in mathematical language is called S2. It's the space of a sphere, space in the surface of a sphere. As it's clear that this is actually a two-dimensional space. If you're on the surface of a sphere, you can move in two directions. And this is a two-dimensional manifold. I'll explain what that means in a bit. So that's an interesting point here. Okay. So this way of thinking about spins is actually a very useful tool. So this was used by Haldane, for instance, in his Nobel Prize winning work. Okay. So Haldane, for instance, was thinking about an antiferromagnet, a line of spins, a chain of spins, and each of them, so you can think of that as being composed of dimers. So first pair of spin, then that's coupled to the next pair, that's coupled to the next pair, and so on. So the entire system is at very low temperature, or very low energies. Then each of them must have 0 energy. Then you must say this pair must correspond to some state like that. So the first spin can point in any direction, second direction is the opposite, second spin is opposite. The second dimer again, first spin points in some direction, and so on. So each dimer maps to a point on a sphere. And then Haldane argued that that field should vary smoothly and slowly. So you might say this dimer maps to one point on the sphere, the next dimer maps to a point that's not very far, third dimer maps to a point that's not very far, and so on. And with that, he could build the field theory that describes these one-dimensional antiferromagnets, and which led to many important results later on. Okay. So we are only considering these small clusters in this talk, but this is just to tell you that thinking of small clusters is a good starting point to understand macroscopic magnets. If you want to understand a big magnet, you have to start with the building block. Right? Good. So now let's go to the 3-spin case. So here is again a triangle. Now I have 3 spins. They must add to 0. Okay? The length is uniform, it's the same length. If you think about it a little bit, you see that there's actually a very strong constraint. How can 3 spins add to 0? There's actually only one way. All 3 spins must lie on the same plane, and if you have one spin pointing up, the other 2 spins must form a triangle. So the angle between these two should be 120 degrees, angle between these two should be 120 degrees, and this two should be 120 degrees. So the only way for 3 spins to add to 0 is they should lie in a plane and they should form the sides of an equilateral triangle. Only then they can add to 0. Okay. Good. So that's a ground state. Any such state is a ground state. Now the next question you can ask is how many such ground states are there? Okay. How many ways can 3 spins add to 0? So then the answer is again simple. So you take one such configuration and you rotate it in any possible way. So suppose you started out with this in this plane, then you rotate it, it might look like this. Okay. You turn the plane, make it look like this. Okay. And once again, you'll get another configuration in which the total spin is 0. Okay. So the claim is every possible state, every state in which 3 spins add to 0 can be obtained starting from one such state and by rotating all the spins. Or you can imagine that you take one particular configuration, you just turn your reference coordinates, you turn your head, and you get a new configuration, and that also satisfies the total sum being 0. Okay. And that exhausts all possibilities. There's no other way. Okay. So the upshot of this is that the sum total of all possibilities for 3 spins to add to 0 is actually the number of possible rotations you can have in 3-dimensional space. You can rotate in many different ways. Okay. In mathematical terms, the set of all ground states is isomorphic to SO3, the set of all rotations. So this is essentially it's just all possible rotations. Good. So, of course, a rotation is how you describe a rotor. A rotor is something like, you can imagine a ball with fixed center of mass, but that's free to rotate. Okay. So then you describe its state at any given time by using a rotation. Let's say at this given time it's rotated by this much, that much. So a set of 3 spins at low energies maps to a rotor. So this is also very well known. This is known since the 1980s, this very beautiful paper. And this again has been used to study a wide variety of magnets. For instance, triangular lattice antiferromagnets can be studied using this. So 1989, Dombre-Reid showed that Suppose you have this is a section of a triangular lattice. You have spins at corners. If you want to understand its low temperature properties, you start with a single triangle and you say this single triangle must be in a zero energy state. It must have 3 spins adding to 0. So it must be in one configuration of the rotor. The next triangle is also in a configuration of a rotor. The next triangle is in a configuration of the rotor and so on. So you get a rotor valued field theory. Okay, so you can imagine, you can map this to a problem where you have these rotors in space and the rotation is always smoothly varying. Good. So that was 3 spins. Okay, so this is all well known. So we started looking at this. We came at it from some complicated direction, but at the end of it, we figured out that if you have the same problem with 4 spins, the answer was not known. Okay. So imagine you have spins on a tetrahedron, so you have 4 spins, and again I have this condition that at the lowest possible energy, all spins must add to 0. Okay. How can you do that? So let's just do some simple mathematics. So if initially I say I have 4 spins, then each spin can be described by 2 variables, right? If I have to describe the state of this spin, I have to give you one angle like this and one angle like that, theta phi. Okay. So I have 4 such spins, so there are 8 degrees of freedom. Each has 2. Okay. And now I say the total spin is 0, which means total x component is 0, total y component is 0, total z component is 0. So that's 3 constraints. So you might say 8 degrees of freedom, 3 constraints. So the total number of ground states where 4 spins add to 0 must be a 5-dimensional space. Okay. That's the counting. Okay. And let me show you how you could actually set this up. Okay. So the answer will be surprising. So just follow with me for this bit. Okay. So suppose I have 4 spins and I want their sum to be 0. I can do something like this. I can say, let me first choose all spins to lie in one plane. And I'll choose S1 and S3 to be opposite to each other, and S2 and S4 to be opposite. And I'll choose the angle between this to be theta. Let's say I fix it as some angle theta. Okay. Now clearly the sum of 4 spins is 0, because 1 and 3 cancel each other, 2 and 4 cancel each other. Okay. But this is not the only allowed thing, the only allowed degree of freedom. What I can now do is I can take S1 and S2, they lie in one plane, and 3 and 4 lie in one plane, and now I can twist them. So imagine I move 1 and 2 this way and 3 and 4 this way. The sum is still 0. You can just convince yourself that the sum is still 0. Because the resultant of 1 and 2 doesn't change, the result of 3 and 4 doesn't change. Okay. And the amount by which I twist is some angle phi. Okay. So I can give you 2 degrees of freedom, theta phi, and I can specify a configuration where spins add to 0. And of course, I can now do an overall rotation. I can look at this in any possible way. An overall rotation takes 3 degrees of freedom. So you have 2 angles and 3 degrees of freedom, that's 5. Okay. Another simple way of looking at it is, suppose I have to add 4 spins, then they must add to 0. In vector language, essentially I have to draw 4 vectors head to tail, and their sum should be 0. So I should form some kind of a quadrilateral. They're all equal length, so I should actually form a rhombus. So if I have to have 4 spins that add to 0, I must form a rhombus. And how many ways can I form a rhombus? So it turns out you need not just form a rhombus. First of all, you can make a rhombus with different angles. You can make a fat rhombus. You can make a thin rhombus. There are many choices. The second thing you can do is you can take these 2 spins alone. So imagine I take these 2 spins, only these 2, and I tilt them out of the plane like this. Okay. Even then the 4 spins will add to 0. You start from here, go up, come back, come back. So 4 spins, 4 vectors will add to 0. So these are 2 angles. One is theta and one is the amount of twist you get. That's phi. And then the entire configuration can be rotated. Okay. I can look at it from any point of view. So that gives me another 3. So that's the set of all possible ground states. Okay. Good. So let me just try to tell you why this is an interesting problem. So right now I've told you that if I consider 4 spins and I demand that their sum must be 0, I need 2 angles to describe it and 3 angles to do an overall rotation. Okay. This seems innocuous, but it's actually not. So let me just try to explain to you why this is not. Let me first skip to the result. Okay. The result is this. The result is the resulting space that you get looks something like this. This is a cartoon for that space. Generically, that space is 5-dimensional, okay, except at certain singular points, that space curves in on itself, it intersects with itself, and gives rise to 6 dimensions locally. So here the space looks 5-dimensional, there it looks 6-dimensional. Okay. So the space, the dimension of the space changes. Okay. So in some very crude analogy, this is like puncturing a hole through a sphere. You go from the top to the bottom, just by jumping across. So these are singularities in the space. So it's a very simple problem that has very nice singular structures. So maybe let me just try to explain this to you with some, okay, let me just try to convince you that this is true. So suppose I have some generic state. So this is a state where the 4 spins add to 0. So here are four spins. Let's say they add to 0 from this way. Now let me ask, in how many ways can I deform the state such that I'm still in the ground state? Okay. So I want to make small changes such that then the sum is still 0. Okay. So here are 5 ways I can do that. Okay. So the first way is I can increase this theta angle. I can pull up the first 2 spins and second 2 spins. I can make them wider apart. That will still keep the total to be 0. The next thing I can do is I can twist the spins, as I said. I can increase the twist angle. If I twist this spins again, the sum is 0. Okay, so that's an allowed deformation. Okay. And the next 3 things are just overall rotations. I can take this, I can rotate about the x-axis, I can rotate about the y-axis, I rotate about the z-axis independently. So there are 5 independent deformations that keep me within the ground state space. So if I'm in a certain configuration where the sum is 0, I can make 5 independent deformations where the sum remains 0. In other words, this space is 5-dimensional. Okay, that's one way to look at it. However, there are special states. So for instance, this is a collinear state. 2 spins are up, 2 spins are down. About this state, I can actually make 6 deformations that keep me within that space. Okay? So here are 2 examples. So let's say the spins are pointing along the z direction, 2z to minus z. Then I can do a rotation about x or a rotation about y. A rotation about z doesn't do anything, just retains the same spins. Okay. And then I can do 4 types of deformations. I can take the 2 spins on top and I can move them apart like this or like that. And the 2 spins on the bottom, I can move them apart like this or like this. So I can do this independently. So that gives me 4 deformations. So you can just convince yourself very easily that there are actually 4 possible configurations. So this is what tells us that at these singular points, this space actually looks 6-dimensional. Okay, so the model of the story is you have a space. So at low energies, this system maps to a 5-dimensional object generically, but that object has singularities where it appears 6-dimensional. Okay, good. So then with Shankar, what we figured out, or Shankar actually helped a lot in clarifying this, in whittling down the problem. We came up with many nice ideas. So what we figured out is that the set of such points, the singularities, are actually very small in number. They're a subset of measure 0. So because they're so small, you can essentially just ignore these points. Just forget the fact that these points exist. You can ignore them and go ahead and try to do an analysis. Okay. So you just think of the system as 5-dimensional. And the result we get is actually very surprising. So let me just tell you the final answer. So that it's done in the language of path integrals. So we show that the partition function that describes the 4 spins at low energies looks like a product of 2 different partition functions. Okay. So one partition function is simply a partition function of a rotor. It's an object that is free to rotate, but the center of mass is fixed. And the second partition function is the partition function of a free spin. A spin is a quantum mechanical spin. It's an angular momentum. Okay. And this spin is an emergent spin. It's not there in the microscopic description. It's just these 2 angles, the theta angle and the phi angle together, take the form of a spin. So the 4 spins together at low energies take a very different form. Okay. This is the notion of emergence that we usually say. You can have a complicated macroscopic object, imagine with some interactions, but you look at it at very low energies, it can take a very different shape, or it can take a very different form. So here we started out with 4 spins. We look at it at low energies. It looks like one object that's rotating and an independent object that's just a spin, that's an angular momentum. Okay. This is an unexpected result, but it turns out it's true. So here, for instance, this is another way that Shankar showed that we could actually demonstrate this. So this is some quantum mechanical results. So imagine we are adding 4 spins using quantum mechanics. We'll get the spectrum in this way. So we'll say that the ground state is energy 0, first excited state is 2j, second excited state is 6j, and so on. And then we'll say that the ground state has 2s plus 1 states, where s is the spin quantum number. First excited state is 3 squared, 2s plus 1 minus 9, and so on. Now if you think of it as just one object that's a rotor and one object that's a spin, and this only comes out of the analysis, very hard to guess beforehand. In that case, you'll say that the energy looks like this. So the spin is free, so it gives you 0 energy. The rotor gives you energy 0, 2j, 6j. So you see that the energy is here and the energies here match. So the 4 spins together really do behave like a rotor and a spin. And the degeneracy of each level also matches, apart from some small corrections. And those corrections have to do with the fact, possibly, that we have those singularities in the space that we're ignoring in this approach. Good? Okay. So maybe with this, I'll just move on to a slightly different problem that is inspired by some of the things we learned from Shankar. Okay. So I'll just quickly just summarize these results. Okay. So now, in the next work, what we've done is we've tried to state a general principle, which I hope will be accessible to all. So the statement is this. So at low energies, the physics of a quantum spin cluster, okay, I'll explain what that is, maps to that of a single particle moving on the corresponding classical ground state space. So this is a statement that we have tried to prove. So we say that you take any system of spins, for instance, a cluster like this or a cluster like that, a triangular cluster or tetrahedral cluster, then you say you're only interested in the low energy physics of this. In that case, and this is actually an interacting problem, it's a hard problem to solve. But in that case, you can simply make an analogy to a single particle moving in some space, and that space is a space of ground states. So this is a statement that we've shown. So let me just show you one example and end with that. So I will skip this part. So good. So here is the simplest case. So it's just an XY dimer. So suppose I have 2 spins, and the coupling between them is purely an XY coupling, which is only the XY plane component of the spins are dotted, not the Z component. Okay. So you can ask, what's the classical ground state of this? Classical ground state is the first spin. So let's say this is the XY plane. Let's say this is X, this is Y. So first spin can point in any direction within this plane. Second spin is completely opposite to it. So that's a classical ground state. That's how you can minimize the energy. So now you can ask, how many ways can you do this? You can actually put the first spin anywhere on this circle. You can change this angle phi, you can put it somewhere there, and the second spin will follow. So the set of all ground states is equal to a circle. You can have the first spin anywhere here. So the set of all ground states is equal simply to a circle. Okay. So now our principle comes into play. It tells us that you take this quantum problem of 2 spins that are interacting. This is a hard problem, since it's a non-integrable problem. You have to actually solve it. Okay. So you take this quantum spin problem, you look at the low energy physics of it, it simply maps to a single particle moving on a circle. Okay, that's our statement. So let me just show you the proof for it. And here is the proof in one slide. Okay. So this is the spectrum for spins. So this is evaluated for different spin quantum numbers. Don't worry too much about it if you aren't familiar with this. So suppose you take spin 9. Okay. So you solve this problem, and you have to solve it in a computer. You can't solve it by hand. So you see that there is a 1 ground state, the 2 excited states, then the first excited state again has 2 states, again 2 states, 2 states, 2 states, 2 states. So this is like the hydrogen atom spectrum. There's a ground state, there are excited states. Okay. But remarkably, you look at the spectrum and you just scale it by some number. You just scale it by, change the units essentially. Then you see that the ground state has energy 0, first excited state has energy 1, second has energy 4, 9, 16, 25, 36, 49. So, okay. But these are just integer squares. So it's 0 square, 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square. And this is precisely the energy of a particle moving on a circle. Okay. So this is what this demonstrates. Good. Good. So we've built on this. We've constructed more complicated clusters. We've shown that very interesting physics can emerge from this. So maybe let me just tell you the punchline. The punchline is this. So you take again a tetrahedron, 4 spins, but now you say the spins are XY spins. They're in plane. They're not allowed to come out of the plane. Okay. And then you ask, what's the ground state space? How many ways can you do this? The ground state space looks like this. Okay. So there is some things I've skipped here, but take my word for this. So ground state space is actually consists of 3 tori. So this is a cross section. So since I'm from Chennai, you're from Chennai, you can say it's 3 vadas, okay, 3 big vadas. So this is a big vada, it's a cross section. And inside it there are 2 vadas sitting. So this vada touches this vada at one point. This vada and this vada touch at one point. This vada and this vada touch at one point. Actually these are lines. This line goes and comes out there. Okay. Okay, so they touch across 2 points. So this space again you see is not a well-defined manifold. So here it looks two-dimensional, but at these points the dimensionality cannot be well-defined. So it's a non-manifold space. Yeah. So here we find some interesting effect. What we see is that, let me just skip lots of details. What we see is that if a particle is to move in this space, it gets stuck to those lines where the space intersects with itself. So the particle gets stuck to singularities. So we call this effect order by singularity, and we claim that this physics can be seen in a magnet with 4 spins. Okay. Good. Okay. So maybe with that I'll stop. I think I have a summary slide, and yes, maybe with this I'll end. So thank you very much. So Shankar, wish you a very healthy 60 years from now.